Hello everyone, my name is Miki Trigoni and I'm a professor of computer science at the University of Oxford. I lead the Cyber Physical Systems group alongside my colleagues Andrew Markham, Alex Rogers and Tam Vu. Our research focuses on intelligent and autonomous sensor systems with applications in healthcare, energy, smart cities and emergency response. We work with novel sensor modalities and we develop algorithms from low-level signal processing all the way to high-level inference and learning and decision-making. At this point, it's a great pleasure to introduce my colleague, Dr. Yao Wei Yun. He's the head of the Department of Robotics and Autonomous Systems at the Institute for Infocom Research at A-STAR in Singapore.
Nice meeting you, Nikki. I'm Wei Yun Yao from the Institute for Infocom Research, HMC for Science, Technology and Research at Singapore. I'm the head of department for the Robotics and Autonomous Systems. In the department, our key interest is to develop robotic solutions that can be used in the real world, looking into how robots can be autonomous, serving human and collaborating with humans. Right? And we look forward to ways to collaborate with Nikki's team.
So today I would like to focus on one of our research areas, which is autonomous systems for emergency response applications. Cyber-physical systems in general have a huge potential to transform the way we live and the way we experience the workplace, ranging from environments such as hospitals to transport hubs to warehouses. But specifically, I'm particularly excited about the emergency response application because it presents unique challenges, but it also has the potential to save lives. The unique research challenges in this context are, first, that the emergency team, they need to be able to localize themselves in GPS-denied environments. And the second big challenge is they need to have continuous situation awareness. They need to be able to understand the scene. And in more advanced autonomous scenarios, we have also the need for person-robot interaction. And all these algorithms need to run on wearable devices at the edge because network conditions in emergency scenarios are typically quite poor. In terms of being able to build systems, location systems in GPS-denied environments that work reliably everywhere, this presents huge challenges. Not only can we not rely on existing infrastructure, but we also have to address the need for diverse motion patterns of emergency responders. And we cannot rely on the presence either of a signal map that can help us with localization, or sometimes even on physical maps, which are missing. And on top of all this, we have to be sort of robust to adverse conditions such as thick smoke, fire, and so on. The first requirement for infrastructure-free localization is not unique to emergency response. We've been deploying for a while systems, infrastructure-free scalable systems in places like hospitals, but we've been using wearables, off-the-shelf wearables such as smartphones, smartwatches, and glasses. Very, very different types of sensors and devices apply in emergency response scenario. We have sensors attached to boots, but we also have mounted sensors on the head, and this could be ranged from inertial to sensors that are robust to challenging conditions, such as thermal cameras and millimeter wave radar. Taking my favorite sensor, inertial sensor, to start with, it is fantastic because it is inherently egocentric and it is not affected by environmental conditions. However, it presents the problem that you have to make inertial odometry robust to attachment changes. When the device is handheld or in a pocket or in a bag or in a trolley, the signals that the device emits are very, very different in body frame. So we've been developing in the last 6 years robust signal processing as well as deep learning-based techniques and domain transformation techniques in order to address this problem. In emergency response scenarios, we have the benefit we can attach those sensors on the boot, and this allows us to apply zero velocity updates, which kind of limits the drift from inertial odometry. However, detecting when to apply these zero velocity updates is very challenging because of diverse attachments to the foot, as well as the diverse motion patterns in emergency response. And we're working on adaptive mechanisms of thresholding for detecting when to apply zero velocity updates. Another way to improve robustness is through sensor fusion. So why not take inertial data and combine it with visual data when we have good light conditions? We've been working in this area, and what we have proposed is a selective sensor fusion approach that combines inertial and visual data at intermediate feature representation layers, either with soft fusion or hard fusion. And the benefit of those techniques is that you can automatically provide time synchronization and calibration of the two types of sensor without manual effort. However, in low visibility conditions, which are very common in emergency scenarios, you can't rely on RGB images. So different types of sensors like millimeter wave radar or thermal images, as you see here, are more functional in dark or smoke-filled environments. However, they lack robust visual features that we are used to with RGB odometry. So what we are doing, one of the ideas we have been developing is the idea of hallucinating visual features from thermal images and fusing again inertial with thermal data and applying selective fusion techniques in order to estimate pose in really challenging these times environments, which are smoke-filled and where even LiDAR does not work well. Another key challenge that we face is that real-time navigation in emergency response needs to be low latency. And these algorithms, if we wanted to take high frame rate data and send it to a server for processing, it would be very difficult, not only because we have poor network conditions, but we also worry about privacy and security in these kind of settings. So we have been working on distillation and model compression algorithms in order to embed those algorithms on devices such as the one that's shown here. And we've been able to get suitable frames per second, like 10 to 20 frames per second data rates for thermal inertial and millimeter wave radar odometry. Another big challenge in emergency scenarios is the lack of signal maps and physical maps. In other more benign applications, we have good experience building pipelines in the group and in a spin-out of Oxford called Navenio, where we can crowdsource signal maps that you see on the left and experience maps that you see on the right with signal maps from people moving around the building. However, in emergency scenarios, we don't have enough users, and we have typically a handful, 2 or 3 emergency responders that are deployed at a time. So there we need to be able to robustly localize a person with respect to trajectories of very few of the other team members that have first gone inside the building, using the concept of experience-based navigation indoors. Also, as people are deployed in emergency scenarios, we have a fundamental need to organically grow the map of the environment. And we have recently developed a system which can see through smoke using very low-cost millimeter wave radar sensors. Not only can we create dense patches of the environment, dense grid map representations of the environment, similar to the ones that would be created by LiDAR, which is a very expensive sensor. But we are also able, in a second inference stream, to provide semantic mapping information, so understand what types of objects we see in the environment. Another aspect of scene understanding is the ability to reconstruct the shape of the objects that we see. But in this case, in emergency scenarios, we don't have the luxury to go around an object and see it from multiple views. So we've been working on single depth view 3D object reconstruction, as well as reconstruction from very, very few RGB images. And we have done that successfully in benign applications, but we're very, very excited to see how this can apply in emergency scenarios. Another aspect, particularly important for emergency scenarios, led by Professor Andrew Markham, is the ability to infer body deformation. So when you're sending vehicles inside an emergency scenario, can you predict, based on single RGB depth images, how, as they traverse an area, surfaces will be deformed under the pressure of those vehicles, whether they're going to be deformed or whether they are going to crack. And we've developed adversarial neural networks, generative adversarial neural networks, capable of predicting that in real time, which is particularly suitable for emergency applications, and having been trained by finite element model simulators. A different aspect of scene understanding in emergency scenarios, also very important, is to be able to understand, to create first coherent point cloud maps of the environment, both indoors and outdoors, and then segment the environment and be able to understand which objects are of which type. So, for example, floor, beam, door, window, clutter, and so on. And similarly, there is a great need for semantic segmentation outdoors to be able to understand the area around an emergency situation. For example, the trees, the buildings, the roads, the traffic signs, the parked vehicles, and so on and so forth. And although we've been very successful doing that with data sets, available data sets that are in benign environments, we have the research challenge that we lack training data that are particular for emergency situations and can identify hazards and other objects of interest to emergency responders. So, to summarize, we have been working on autonomy in the workplace, and 5 years ago, we established a spin-out from the University of Oxford Navenio, and now we have algorithms working and improving efficiency in places like hospitals, in benign environments. My dream and vision here is to build cutting-edge research and bring it to a level of maturity where we can address much more challenging applications, such as emergency situations. And I'm very hopeful and positive about this because we have amazing support through an international collaboration funded by NIST, EPSRC, and more recently Amazon, and the very exciting Oxford-Singapore Human-Machine Collaboration Initiative. So at this point, I would like to thank you very much for your attention and thank my colleague and close collaborator, Andrew Markham, as well as members of the CPS group and the funding bodies that have enabled that research.
So what I will do is that, I will give a short introduction about ASTAR, as well as the Robotics and Autonomous Systems Department. Right, a brief overview is ASTAR, or Agency for Science, Technology and Research. We are a statutory board under the Ministry of Trade and Industry. So ASTAR's vision is to be the catalyst and enabler, as well as convener of a significant research initiatives among the research community in Singapore and beyond. Right? And here, ASTAR also collaborates with both public and private sectors to bring science and technology to benefit the economy and society. In ASTAR itself, we have two key councils. We call it the Biomedical, or BMRC in brief, as well as the Science Engineering, or SERC. And in SERC, we have a total of 8 research institutes, one of which is the Institute for Infocom Research. So under the Institute for Infocom Research, this is the structure that we have. If you notice, there is altogether 7 departments. We are in a matrix structure, so we have divisions. Divisions target a certain key focus areas. For departments, we are more on capabilities. One of the departments is Robotics and Autonomous Systems, which I'm heading. Right. So a short introduction about our department. We focus on service robotics, other than those industrial robotics. And one of the key areas that we look at is service robots that's relevant for Smart Nation. So we look into how can we have robots that can perform autonomous operation in a dynamic, unstructured environment, especially in Singapore weather, right? We have tropical weather, so heavy rain is a big problem for us. And in the service robots, we do often require that robots work with human or assist human as a team. And that is the focus that we have. In terms of key research scope, we have areas like autonomous navigation, perception, manipulation, human-robot interaction, human-robot collaboration, the learning aspect, as well as system integration and prototype. In terms of collaboration, obviously, we do collaborate with universities, as both local as well as abroad, government agencies, as well as a company. One of the key highlights is that these are our research focus areas, navigation, manipulation, perception, and material collaboration. I won't go to the detail, but the focus is that these are challenges that I believe is common and something that of interest to Nikki as well. And in terms of application domain focus, we primarily look in healthcare, and one of the area of common interest will be safety and security, which we are also a lot focused on. Autonomous inspection, as well as recently we have agri-tech, right? These are sample projects we had. These are sample projects where we collaborate with government agencies because of their need. And then we also involve private sectors or companies so that the solution will be able to be provided to the government as end users. One example is in the area of security surveillance system. Here we develop autonomous robots that can move in both indoor and outdoor to do patrolling, especially after office hour. Right. The example here is done during the National Day Parade. The middle project is basically the key idea is how can we enable a more autonomous operation to authenticate users when they drive through from Singapore to our northern neighbor, right? So this is a project that we collaborate with companies to satisfy the need of the Immigration and Checkpoint Authority. And what we focus on is robotic capability, while the company look into the whole system integration. And the idea is that we bring the authentication device to the four sides of the vehicle so that the passenger don't have to leave the vehicle. And they can authenticate, just like in the airport, right? You can authenticate your passport with the biometrics like face and fingerprint. And to the right is a project we do with the Changi General Hospital to allow robots to operate inside the hospital ward. One of the key challenge is how does the robot able to understand some of the challenging dynamic environment, like for example, the beds are being pushed around, the curtains being closed. The robot must survive in such environment, and most importantly, to understand emergency situation, such as when there's we call it code red or code blue, the robot must give way and not to obstruct the path of people to evacuate. When there is a need, when the nurse push the bed, the robot also must give way, right? So that the patient will have priority. So these are some challenges that we are solving, and obviously some of these will require semantics information, right? So these are some examples where we also involve a researcher, for example, from National University of Singapore, the Nanyang Technological University, which are the university part, us, the hospital, and eventually private companies, right? When we have developed a solution, right? That's all I have. Thank you very much, and yeah, we'd be more happy to discuss with Nikki. There's a lot of common interest, so I'm very excited. Yes, yeah, definitely.
I'm extremely enthusiastic myself. I mean, I think in the sense of there are huge challenges to improve the quality of life of people everywhere, both at work and at home in the future. We have to basically increasingly develop unsupervised algorithms that do not rely on ground truth data, on labeled data. but can benefit from the fact that we have increasingly sophisticated sensors and the ability to detect data at higher sort of granularities than we had ever before. So this is like a very exciting research direction, and doing sort of experiments in the wild, in real world settings, is something that I find very, very appealing.
I think this is a very interesting topic of research. I think there's a good opportunity because typically most of the big data, one of the biggest problem or the most expensive problem is how do you get the ground truth. And when you deploy people to do the labeling, right, it's very, very expensive. Right? I think this type of research, we have in our institute a department on machine, we call it machine interaction. So they are one of the few research areas they are looking at is including how do you learn from noisy data, incomplete data. I think these are some areas that I think there's a potential for multi-party collaboration, definitely. Yeah.
Sounds great. Thank you very, very much for your time. It was a real pleasure that to find out more of what you guys are doing in Singapore. I look forward to opportunities for collaboration. I think that to me, the hospital environment and being able to combine people perception of, human localization, robotic navigation, and potentially even other aspects of physiological sensing that we are doing in the group. If we could combine a number of different diverse technologies in a hospital sort of environment, this would be, I think, a really great start. And then if you are interested in getting involved in our international project for emergency response, we're very, very welcome to have you as an international partner there and engage more closely as well.
It's something that we definitely look forward to. I think in these areas, what we hope is that eventually through the collaboration, we will speed up the deployment of the technology in the real world. I'm sure sometimes a challenging environment in the UK may be different in Singapore, or may some differences in Singapore, and hopefully this will also promote ability for technology to be deployed in the world quickly through multi-party collaboration and multi-nation collaboration.
Sounds great.
Sounds great.
Many thanks.